Hello again. We just finished doing lines 15A, B, B2, C, D, D2, E, and F. And now we're on line 16, and I've had to divide it into two videos because there's quite a bit of information that comes up. So I've got line 16A and line 16B. Okay? So today is January the 20th. It's 2:32 p.m. I just finished doing some more research on this and typing some notes up. I took a look at the data real quick, okay? So line 16A is going to be called Stereographic Projection Time Lapse Function Spherical Plucker Coordinates Euclidean Minkowski Space. The equation is over here on the SETI signal from 1977. It's this big long equation here, okay? So what we did 51 divided by 14 divided by 3 divided by 4 divided by 4 divided by 1 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 divided by 11 equals 0.0001. Okay, so there. Now I'm just going to show you real quickly what's going to come up in line 16A. Mathematical equation, stereographic projection time lapse, function mathematics, geographical coordinate systems, cylindrical and spherical coordinate systems, Plucker coordinates, Euclidean space, Minkowski space. In line B, we're going to talk about the theory of special relativity of Einstein, superluminal neutrinos, hyperbolas, neutrinos travel faster than the speed of light, conservation of momentum, kinetic energy of the muon, not moon, it's muon, the OPAL experiment at ALEPH 1989 to 2000, and the OPAL and Muon detector. Okay. So for line 16A, the first thing that came up with that equation was the stereographic projection time lapse, MPVN, and there's the number there, 0.0001 by Blind Summit. It was vimeo.com 294-51315. So of course I had no idea what it was, so I googled it, and this is the diagram that came up. Some sort of projection box or something. Graphical projection it's called. Okay, that's what it looks like there. So the stereographic projection time lapse is, actually I'll show you this video here. I found this on YouTube under Blind Summit Films. He shows what a time lapse looks like. Okay, you can go to his YouTube video to look at it. I'll have the link up there for you. The quote is, "What makes this technique even more interesting is the fact that by increasing the intervals between the shots, it's possible to demonstrate unnoticed events that take time in seconds." That's called shutterexperiments.com. Okay, this 3D illustration is of a stereographic projection from the North Pole onto a plane below the sphere. So there's your North Pole, and then there's the projection, and this is another plane here. The stereographic projection in geometry is a particular mapping function that projects a sphere onto a plane. The projection is defined on the entire sphere except at one point, the projection point. Where it is defined in mapping is smooth and bijective. It is conformal, meaning that it preserves angles. It is neither isometric nor area preserving. That is, it preserves neither distances nor the areas of figures. Intuitively then, the stereographic projection is a way of picturing the sphere as the plane with some inevitable compromises. Because the sphere and the plane appear in many areas of mathematics and its applications, so does the stereographic projection. It finds use in diverse fields including complex analysis, cartography, geology, and photography. In practice, the projection is carried out by computer or by hand using a special kind of graph paper called a stereonet or wolfnet. And that's under Wiki under stereographical projection. Next came up was function mathematics from Wikipedia. So I looked it up to see what a graph of example function looks like. In mathematics, a function associates one quantity, the argument of the function, also known as the input, with another quantity, the value of the function, also known as the output. Okay, so it talks about numbers and equations, and that's under wiki function mathematics. The next thing that came up was the coordinate system. So coordinates for geographical coordinates. In geometry, a coordinate system is a system which uses one or more numbers or coordinates to uniquely determine the position of a point or other geometric element. The order of the coordinates is significant that they are sometimes identified by their position in an order tuply, and sometimes by a letter, as in the x-coordinate. In elementary mathematics, the coordinates are taken to be real numbers, but in more advanced applications, coordinates can be taken to be complex numbers or elements of a more abstract system, such as commutative ring. The use of a coordinate system allows problems in geometry to be translated into problems about numbers and vice versa. This is the basis of analytic geometry. An example in everyday use is the system of assigning longitude and latitude to geographical locations. In physics, a coordinate system used to describe points in space is called a frame of reference. So the frame of reference is, you know, where we talked about the Mayan planet being at 22 hours, 57 minutes, so many seconds. That's a time frame on the star charts. Okay? So cylindrical and spherical coordinate systems. So this is cylindrical coordinate system and spherical coordinate system. There are two common methods for extending the polar coordinate system to 3 dimensions. So it's back to that graph there, where you've got the North Pole being projected onto a plane. In the cylindrical coordinate system, a z-coordinate with the same meaning as in Cartesian coordinates is added to the r and 0 polar coordinates. Spherical coordinates take this a step further by converting the pair of cylindrical coordinates, r and z, to polar coordinates, p and 0, giving a triple pvx. Now, I kept seeing these symbols. I didn't know what they meant. So that's something we can look to in the future, coordinates, okay? And then up came Plucker coordinates. In geometry, Plucker coordinates, introduced by Julius Plucker in the 19th century, are a way to assign 6 homogeneous coordinates to each line in projective 3 space, P3. Because they satisfy a quadratic constraint, they establish a one-to-one correspondence between the 4-dimensional space of lines in P3 and points on a quadratic in P5, projective 5 space. A predecessor and special case of Grassmann coordinates, which describe k-dimensional linear subspaces or flats in an n-dimensional Euclidean space, Plucker coordinates arise naturally in geometric algebra. They have been proven useful for computer graphics and also can be extended to coordinate for the screws and wrenches in the theory of kinematics used for robot control. Now, you'd want to use some sort of robot stuff in a UFO, right? For outside repairs and stuff. This is Julius Plucker. Okay? He was born June 16th, 1801, and he died May 22nd, 1868. He was German. His fields were in mathematics. He went to quite a few universities, as you can see. He was an advisor to Christian Ludwig Gerling. He had students studying over him. He's known for the Plucker formula, and he won the Copley Medal Award in 1866. The next man we're going to talk about is Minkowski, Jules Henri Poincare. So let's go over to Euclidean space from Wikipedia. That's what it looks like. That's the graph for it. Every point in the 3-dimensional Euclidean space is determined by 3 coordinates. In mathematics, Euclidean space is the Euclidean plane and 3-dimensional space of Euclidean geometry, as well as the generalizations of these notions to higher dimensions. The term Euclidean distinguishes these spaces from the curved spaces of non-Euclidean geometry and Einstein's general theory of relativity, and is named for the Greek mathematician Euclid of Alexandria. Classical Classical Greek geometry defines the Euclidean plane and Euclidean 3-dimensional space using certain postulates. while the other properties of these spaces were deduced as theorems. In modern mathematics, it is more common to define Euclidean space using Cartesian coordinates. That's another word that came up again. And the ideas of analytic geometry. This approach brings the tools of algebra and calculus to bear on questions of geometry and has the advantage that it generalizes easily to Euclidean spaces of more than 3 dimensions. So this type of algebra would be used for things out in outer space. Okay, so there's more about the space as a tuple of real numbers, and distances are defined using the Euclidean distance formula. Mathematicians often denote the n-dimensional Euclidean space by Rn or sometimes En if they wish to emphasize its Euclidean nature. Oh, so that's what the E stands for. Okay, so you can wiki the Euclidean space to find it. And see, I think I go down here next. Okay, history. In 1905-06, it was noted by Henry Poincare that by taking time to be the imaginary part of the fourth spacetime coordinate B-1 CT, the Lorentz transformation can be regarded as a rotation in a 4-dimensional Euclidean space with 3 real coordinates representing space and 1 imagery coordinate representing time as the 4th dimension. So there's your 3 dimensions, and then they added the 4th one there. This idea was elaborated by Hermann Minkowski. He used it to restate the Maxwell equations in 4 dimensions, showing directly their invariance under Lorentz transformation. He further reformulated in 4 dimensions the then recent theory of special relativity of Einstein. From this, he concluded that time and space should be treated equally, and so arose his concept of events taking place in a unified 4-dimensional space-time continuum. In a further development, he gave an alternative formulation of this idea, which did not use the imaginary time coordinates but represented the 4 variables x, y, z, t of space and time in coordinate form in a 4-dimension affine space. Points in this space correspond to events in space-time. In this space, there is defined the light cone associated with each point. I'm not sure what that means. Minkowski, aware of the fundamental restatement of the theory which he had made, said, "The views of space and time which I wish to lay before you have sprung from the soil of experimental physics, and therein lies their strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." So over here, let's take a look and see who Minkowski is. There's a diagram of his cones that he was talking about. There's the future light cone. This is time going this way. Observer, space, hypersurface of the present space, and past light cone. So that's a diagram showing only 2 of the 3 space-like dimensions. You want to see the Minkowski diagram. I didn't do it. Okay, in physics and mathematics, Minkowski space or Minkowski spacetime, named after the mathematician Hermann Minkowski, is the mathematical setting in which Einstein's theory of special relativity is most conveniently formulated. In this setting, the 3 ordinary dimensions of space are combined with a single dimension of time to form a 4-dimensional manifold for representing space-time. In theoretical physics, Minkowski space is often contrasted with Euclidean space. While Euclidean space has only space-like dimensions, a Minkowski space also has 1 time-like dimension. Therefore, the symmetry group of a Euclidean space is the Euclidean group, and for Minkowski space is in the Poincare group. So all these guys are kind of joined together. The space-time interval between the 2 events. So you can see all their theory is kind of interconnected with each other. This is Hermann Minkowski. He was born June 22nd, 1864, and he died January 12th, 1909. He's German. He was a mathematician, and he went to some universities there and had some students under him. Okay, so you can look at Minkowski. So we're going to be talking more about Einstein's relative theory and how the neutrinos testing in 2012 is questioning his theory, and that's going to be in line 16b video. Okay, so The structure, formerly Minkowski space, is a 4-dimensional real vector space equipped with a non-degenerate symmetric bilinear form with signature minus, plus, plus, plus. Some may also prefer the alternative signature of plus, minus, minus, minus. In general, mathematicians and general relativists prefer the former, while particle physicists tend to use the latter. In other words, Minkowski space is a pseudo-Euclidean space with n equals 4 and n. Okay. And I did my thoughts way up here, and I want to make sure I get them in this video before I run out of time. Okay, so Google. So I googled the stereographic projection timelapse in line 16. So my thoughts: January 9th, 2012, 12:42 p.m. or 12:42 a.m. Eastern Standard Time. I started writing this last night, 12 hours ago, over 12 hours, 14 hours ago. It's now 2:48 p.m. and then I added to it, but I forgot to put the time. So you should know I've been working on this for 24 hours. Based on this Maya message, I always get it mixed up. Maya message, I think they are trying to tell NASA and SETI to slow down the camera to see what they are missing in the Kepler star region. At the moment, they're looking at the spectrum of planets, and it's saying you need to slow down the frames, and you'll find something there. In line 16a, we are introduced to different types of geographical coordinate functions used to measure between planets, UFOs, sightings, star nebulas, solar systems, different galaxies, and other celestial charts and anomalies found in the universe since the beginning of time. The fact that they can build the James Webb telescope and it can tell us how the universe began, well, that fact alone blows my mind. Perhaps we will learn more in the coming videos on just how they can do it. Quote, in this setting, the 3 ordinary dimensions of space are combined with a single dimension of time to form a 4-dimensional manifold for representing a space-time. We learn what makes space and time and what mathematical equations are used to calculate it. Okay, so the next video is going to be 16b. It's a continuation of 16a. And I've got some more stuff coming up here, and hopefully we won't run out of time because I've got 1 bar left.